Well, thanks for being here. My name's Mark Gahegan. I'm a professor in the School of Computer Science here at the university, and I direct the university's Centre for E-Research, and I've been doing that for around 3 years now. So my name's Mark. I'd like to introduce my two colleagues I've brought with me. This is Sina, who's one of our application specialists and does some work on GPUs. And this is Gene. He's an HPC specialist and mathematician, and does work on our high-performance computing and job submission and code optimization kinds of things. So when it's a hard technical question, those guys will be answering it. And when it's an easy big picture question, I'll be answering it. So please do ask questions as we go. So let me start. Putting aside my own research interests, and I've talked to people at ABI about those before, so I'm not going to talk about those today. Putting those aside, I direct the Centre for E-Research at the university. And one of the things that I worked on for 3 years, as soon as I arrived in New Zealand 4 years ago, was a thing that's become the national e-science infrastructure. This is the government's $47 million investment, the government and the sector's $47 million investment in high-performance computing and e-science for the country for 3 years, hopefully with ongoing funding after that. And so I led the science case and the investment case to MSI and to the government for that exercise. And it's really because of that we've got a lot more hardware around the country than we had last year. And I'm coming to ABI today to try and interest you in using some of that hardware to explain what it is we've got, to show you a little bit of what we can do and how we're organized, and to encourage you to come along and have a go. Now, around the university, both inside of the National E-Science Infrastructure and outside of it, just as the Centre for E-Research, we have about 60 or 70 researchers around the university who are working with us on various projects. We have about 45 projects currently undergo. We just passed, or are about to pass over the weekend, we hope, a million CPU hours served up on our new cluster since it became operational in January this year. But what we don't have is a lot of use from the ABI. And since this is a massive collection of researchers by any university standard, then I'm keen to try and make some inroads and get some use here. So ask any questions that you have as we go along. I'm going to talk a little bit about what the National E-Science Infrastructure is, and what equipment we have, and how we organize ourselves, and I'll get these two guys here to talk in a little bit more detail if that's what you want. Ask any questions as you go along about any aspect of this you don't understand, please. Now hopefully this works from over here. Yes. So NeSI, as we affectionately call it, has two major set of aims. To create an advanced, scalable computing infrastructure for the whole of the nation. So the idea here is that every institution in New Zealand, there are 8 universities and 8 CRIs really, all of them have to have their own compute infrastructure at the moment, and they all have to have their own compute infrastructure teams and planning. And really, we could choose not to compete with each other at that level. We could choose to compete with each other levels above that in terms of researchers. So why not build a research computing infrastructure for the country and share it with everybody, and stop trying to compete in terms of who can spend the most capex? So that's what NeSI does. Well, of the $47 million that we've got to spend, roughly about 27 million of that is from the government, and roughly 21 million is from the institutions, including this institution. We're a big investor in NeSI. That's buying us 3 different compute platforms. There's a compute platform at NIWA, which is part of their IBM P6 infrastructure, the one they use for the climate modeling and the weather forecasting in New Zealand. And there's an IBM Bluegene P, with I think 2 racks of Bluegene P down at Canterbury, at the Blue Fern Group down there, and a smaller IBM P7 machine. And at Auckland we have a commodity Intel cluster, with about 1,000 nodes in it right now, more about that later, and some GPUs and some fast data storage. All of those are part of NeSI, and all of them are available to the sector at large. So any researcher in New Zealand can use that infrastructure now as part of their own research. And there are people in NeSI, like Gene, Sino actually isn't in NeSI, but he helps out with it a lot, who can help move code, write wrappers, whatever it takes to try and get people over the line in terms of using that infrastructure. The University of Auckland has invested quite a lot of money in this infrastructure. We invest about $500,000 a year, but maybe a bit more than that, in actual hardware, which goes into the Intel cluster that we run, my group runs. And as internal University of Auckland researchers, you get to use that without having to pay anything at all. If you want to use the merit access part of NeSI, the part that you have to sort of be a merit-funded researcher for, and the part that extends to the other sites, to NIWA or to Canterbury, then you need to pay about 20% of the cost. So we're creating this scalable infrastructure that goes across the country. You'll notice, if you know anything about high-performance computing, that those three different platforms really cater to three different kinds of high-performance computing. The Power Series computers, I think you guys have owned one of those, haven't you, a P5? Yeah. For SMP style computing, for highly interconnected computational modeling. Then we've got the Blue Gene at Canterbury, which is really a massive amount of CPUs, typically with a smaller clock speed and a smaller amount of memory on board. Very good for embarrassingly parallel tasks, very good for some kinds of deeply connected high-performance computing too. And our own stuff here, which is much more commodity in terms of the fact that it's Intel hardware, but we have GPUs running alongside that too to help some of the scaling of various kinds of research problems. The second aspect to NeSI is a sort of e-research or e-science theme, and that's to provide the middleware, the storage, the applications, and management and user support and community around that hardware. So it's not just a platform and have a go, and if you can't use that platform, it's tough luck. It's more like we'll work with researchers to help you move to those platforms and make the best use of them. So NeSI has platforms, but it also has a community of developers and application support people, and it has a directorate above that that helps to orchestrate the activities across the various sites. And Nick Jones, as some of you will know, is the NeSI overall director. So I direct activities at Auckland as a node in NeSI, if you like, as one of the compute partners. We have a couple of side partners too. It's probably not important to know that, but Landcare and probably Otago will also be investing hardware with us to host at Auckland, so that we scale up a bit more and so that they effectively become our partners co-investing with us. We get more hardware that way. So there's middleware, and there's specific engagement with researchers and research communities, and this is what our guys spend most of their days doing. And manage the continued evolution of this infrastructure. We've got, we're written into the government's plan for long-term research infrastructure funding for the next 9 years now. So assuming nothing drastic goes wrong, we expect NeSI to continue, just like we expect Karen to continue, or NIWA's research vessel to continue to be funded. We're in the same bill. It's gone through Parliament and been approved. So although we have to show value every 3 years or so, so that we can re-access that funds. The funds are there. They've been set aside in a paper, a parliamentary bill. So we're not just providing the compute resources at the bottom. We're providing the middleware and the applications and tools to reach right into the various research communities. So just to give you a quick example, you guys do this all the time, I'm sure, so it's not really an issue for you. You have people who work at the applications level. In our case, this is Jack Flanagan, who's interested in drug discovery. He works in the Maurice Wilkins Centre. He actually works at this university in the medical school. He's interested in molecular docking. And he's got programs like Gold that work on various kinds of hardware platforms. They have various subtasks in them, like X-ray crystallography, gene sequencing, that kind of stuff. We connect all of that together to make a virtual screening pipeline for Jack. So our guys have worked quite hard with Jack to help port his codes on particular environments and provide a pipeline that's easy for him to use. So he's not exposed to the runtime interface of or a secure shell onto an IBM Power 6 machine. He gets a bunch of applications back that he can run from his desktop. We can't do that with every research community, but where there's really good value in doing that, we try to. And we try to encourage researchers like Jack to help fund some of the development work of the middleware and the application programming that might be needed. So in this case, I think Jack funded us about $25,000 to help build those applications for him. So what do we have at Auckland? Well, we started off with 10 8-core nodes in 2006, not very much. Pre-NeSI, last year we had 500 cores in the Best Grid cluster. Some of you might have used that. In the new PAN cluster now we've got 80 compute nodes. It's Intel Westmere, 12 cores, 96 gigs of memory. There's an InfiniBand interconnect across all of that. 200 terabytes of fast parallel disk with GPFS and some dedicated disk controllers. So we don't have any of the current issues with SONAS in ITS, and we have our own dedicated parallel file store. We've got 4 GPU nodes at the moment with Teslas in them, and I know that you guys may be interested in GPU node computing, so maybe we'll talk about that in a moment. We are awaiting delivery now of another 1,000 cores, our second tranche. We're buying, our compute infrastructure gets bigger every year. Our other 2 partners, NeSI had already bought theirs, so we just give them money to buy time on it. And Bluefern bought all of their stuff up front. So they've got a good facility now, and we chose to buy in yearly increments for various reasons, mostly because we wanted to be able to catch the latest developments as they came along and scale up more slowly as the demand increased. So now we've got another 1,000 cores that are about to be delivered. We hope they'll be here by the end of this month or early next month. So that will double the size of our compute platform. That will also involve us moving to Sandy Bridge and to, I think there's 16 more CPUs per node. So 16 CPUs per node rather than 12. But we've scaled the memory at the same rate as this. So there's now 128 gigs of RAM on each node. And we've got 10 more GPU nodes and some more nodes for virtualized services coming along as well. We think that Otago will join us also within the next month. And they'll bring in some capital of their own, which we leverage more government money with. And so we expect by the time we move to the Tamaki data center, which will probably be around September or October, the new university data center, we expect we'll have another 500 to 1,000 more CPU cores that we can add into that mix. So we're looking by the end of the year to have 2,500 cores, and more than that if you count little GPU cores. So it'll be a fairly sizable facility, which we hope that we can interest you guys in using.
Sorry, now what does PAN stand for?
Good question. Thank you. When the computer arrived, we thought that it was the source of all evil in the world because various parts of it didn't work, and we had to learn how to use GPFS and Load Leveler and XCAT, all IBM tools. And so we called it Pandora. Pandora didn't seem like it had good PR possibilities. So when we went into production, we changed it to Pan. So on a bad day, it's Pandora, and on a good day, it's Panache. And we add our own, or it's down the pan, or something like that. We add our own prefix and suffix depending on how things are going.
Actually, it stands for Parallel Architecture for NeSI.
There you go, Parallel Architecture for NeSI, yeah.
Just to cover it.
Yeah. And we don't typically have many bad days now. I think we've been up and stable, except for once when we got our credentials, someone lost their credentials, and so we got hacked by someone in Romania. Our login node got damaged, but we didn't lose any jobs. We're a pretty reliable service, I think. We're also managing to keep some compute jobs running for a very long time, up to 3 months in some cases. So we're quite flexible in what we'll take, and we'll go the extra mile to try and run things that are a little bit strange from a sort of high-performance computing perspective. There are a number of people in our NeSI team at Auckland. We've got systems engineers. We've got 2 people. One is an open position at the moment, but you might know Yuri Halitsky, who's been around for a while. We've got a guy called Marcus Binsteiner, who works on grid middleware and makes job submission easy, particularly for customers who aren't familiar with command lines and shell scripts and that kind of thing. We've got some shared services and virtual machine support, a guy called Aaron, who is a Landcare employee but works as part of our team because Landcare are one of our partners in NeSI. And we've got some science applications people, Jean, as I said, who's a mathematician interested in signal processing, and what should I say, the physics of signals from outer space. We've got Ben, who is a computational chemist in his training and very familiar with computational chemistry in high-performance computing environments. We've got various bits and pieces of talent around the team, people who are interested in geo and chemical and physics applications. No one yet who you might say is a mainstream bioinformatician or biologist, but we hope we might get someone like that next. And we've got a web services person, again an open position we're hoping to fill. And there'll be a couple more people added into that team as Otago come up to speed. So we have got a reasonable group with some fairly specialized skills that mean that we can help users who have more demanding needs, rather than just giving people shell access and telling them to go for it. We can support various kinds of parallel processing. We can run MPI, various kinds of multi-threading codes we can support. Jean will be able to tell you more about that. Do you want to give a quick summary, Jean? Pass you the microphone.
We have, can I do it from here? Yes, we can support multiple parallelization techniques. MPI is our preferred one. We have a number of versions for OpenMPI, and Mark will mention compilers that we have, and we have OpenMPI options for every compiler that we support. We can support PVM if there are needs for that, and Jack Flanagan, his software, Gold, is PVM based, so we can support it. We can support specialized versions for MPI, like MV-APSH, yeah, that's one. We also have support for, it's in beta stage more or less, Portland Group cluster parallelization software. We're still testing it, but it looks like it works fine. And since all our compute nodes are InfiniBand connected, the performance is fairly good. It's not what we want to have finally. It's still being tuned up, but it's much better than plain Ethernet, even 10 gig Ethernet. We also have multi-threading support. OpenMP is fully supported. Custom thread pooling is supported well as well. Load level has a bit of a hiccup in this domain, but we're working on resolving these issues. So.
Yeah, sure. In brief, we basically have 8 GPUs. There's 2 per node, so there's 4 nodes. and they're Tesla M2090s, and they've got 512 cores, and then 6 gigabytes of RAM. We can install the latest CUDA as it comes out. That's not an issue. We can also support OpenCL if anyone uses that.
Yeah, more than doubling that number of GPUs at the next delivery. So we'll have. Repeat the question and then answer.
Debuggers, we have GDB at the moment. We haven't got any parallel debugging capability at the moment, and that's in the plans to get. We support. We plan to get Intel-based debugging support. Not sure when it becomes available, but we are more than keen to have something because we've already developed quite high interest to develop parallel applications properly.
What about total view?
It depends. It depends on what we will be able to get. Total view was on the list. We hope to get it along with the compilers, and we have Intel and Portland Group compilers at the moment, the latest versions of them. But somehow it slipped a bit backwards. So that would be in the next tranche of software that we're going to get for the cluster.
Thanks, Gene. So, excuse me, we can support quite a number of different development environments. We don't, within the NeSI consortium, we don't have money for specific application software for particular communities. If we tried to take that on for the whole of the country, we'd need another zero on the end of the pot of money. But if you've got licenses and code that you want to run, we can connect to license service or run your code on our compute if that circumvents issues with availability for you. Licensing is a real issue, particularly with things like ANSYS and some of the more established environments for simulation and modeling. It's hard to scale up without having licenses scale at the same rate as the hardware, and it's way cheaper to buy cores than it is licenses in many cases. For that reason, and probably that reason alone, we do like open source software, but not everybody can do it yet. Just want to show you that this stuff does scale. This graph here shows some work. Stuart Norris, who was one of our early adopters of our PAN infrastructure, and this shows the speed up that he's getting, solving Navier-Stokes equations, using Fortran 90s, getting a performance of about 1.5 teraflops on 900 cores. It's a fairly complex task, reasonably large mesh that he's simulating over. And you can see that it's scaling as you would expect. The interconnect is working right, and his code parallelizes as well, you might assume from this. But that's just to show that, yeah, you can get nearly 1,000 cores all working together at the moment. And if we dig into the details a little bit, there's the same application 600 times faster on 900 nodes, so he's losing a bit of performance to interconnect speeds and complexities, but it's scaling pretty well. And mostly not quite linear, but it's an explainable and realistic, it approximates linear. And here we can see this is his parallel efficiency, which apart from a major hit when it goes from 1 core to 2 cores, and as it starts to scale, some performance issues, but then it starts to stabilize up just above 0.7, which is great. We wouldn't expect that would continue forever. With algorithms, you always reach choke points as you start to scale to thousands of cores that you didn't expect, didn't anticipate at the start, and aren't necessarily obvious by looking at the code. But as soon as we've got our next 1,000 cores, we'll be running the same simulations again, and we hope that we'll get a straight line, or a straight-ish line, out into the distance somewhere to the right. But we'll see. The best place to go to find out about what we've done already is to our wiki. And that's, if you go to the University of Auckland wiki, wiki.auckland.ac.nz, you'll see that there is a Centre for E-Research has its pages hosted on there. And once you find that, just go to the projects page. That's the best page to look at what we've done for other groups. There's also a page on how to use the various facilities that we have, and pages on the application software and the compilers and tools that we run already. Make sure you log into the wiki, because some of the information is not available to the public. So once you log in using your UOA credentials, you'll see everything. This is just showing you a particular project page for a particular project. It's the Movement Neuroscience Laboratory that we started, I think, quite recently, this one, isn't it? A month or so ago. All I really wanted to show you is that we do keep good documentation of our projects, the people involved, the aims, the background, the current environment those researchers are working in, the requirements that they have, actions, scripts, communications, outcomes. We like to track it all. Then we can go back to the government at the end of the year and say, look at all this great science we enabled. We didn't just make someone in the ABI run 100 times faster, hopefully, but we also helped them produce these major research outcomes, and they got these grants too. And our vice-chancellors all need to see that information to keep investing. So we need to track the outcomes as well as the inputs to our work. So if you work with us, we'll create a project page like this. You'll have a point of contact within eResearch who will be responsive to your needs, and we'll gather some information from you, and we'll make progress on your needs, and you'll see regular updates, and we will try and keep tabs also on what you've done with the work that we've enabled. Here are just some of the projects we have going on at the moment, from all kinds of things to managing collections of biodiversity information in oceans for the Lee Marine Institute, through to collections of historical maps for the New Zealand libraries, through to urban air pollution modelling for folks in the School of Environment, through to early universe cosmology from our new physics professor, Richard Easter, and all kinds of stuff, the evolution of language, statistics, data mining, all kinds of stuff. And there's more on this page too, all kinds of things that we do already for people around the university. There's Stuart Norris on there doing his testing. So there's a reasonable amount of experience in various different kinds of compute environments. There's even the Bioengineering project here that when I checked it out, I was quite disappointed to find it was mostly empty. I think we've tried to work with you guys once or twice before and never really got. Perhaps we couldn't provide the compute that you needed, or I don't know what was missing, but I'm hoping that today we can figure out how to engage with you a little better. As Jean began to explain, we've got an awful lot of software loaded up too, ready to go. We support various groups around the university already. In fact, some groups in the university have already bought hardware to add to our cluster that we run for them free of charge. That's another way of using us. If you decide that you want to invest in your own hardware and you want priority on it, but you don't want to have to run it, then you can give that to us. As long as it fits with the hardware and the way of operationalizing the hardware that we run right now, we'll do that for you. And physics, chemistry, maths, stats, some groups in engineering already do that. We host a number of nodes to different groups around the university, and they get priority on that. And in return for that, when they're not using it, we get a low priority queue onto their hardware that we can distribute to other people. And vice versa, they get a queue back onto the rest of the hardware at a lower priority that they can use when no one else is using it, or some arrangement like that. It means everybody gets more peak capacity than they could manage just with their own investment. And we're sort of flexible as to what actual arrangement you might need. We'll try and work with you on that. Here are some of the software packages we have installed already. As you can see, a lot of work in bioinformatics. Everybody wants to do bioinformatics right now. I think 6 of the 8 CRIs, the Crown Research Institutes, all do bioinformatics. And we support some bioinformatics for various groups, including folks at Landcare. and various departments and research groups around campus. As you can see, there's quite a lot in computational chemistry, some work in engineering and maths as well. And some of this is very esoteric in the way it's set up. Some researchers need Intel commodity hardware, some researchers need GPUs, some researchers need what we might call a FAT, research VM. They need a virtual machine with 512 gigabytes of RAM. So they can do more sort of real-time interactive computing. And we support that too. Not easy, but we do. And we have various custom-built software applications that we've sometimes got involved in building with people. We've got all those compilers there. Jim mentioned some of those already. Runtime environment that we support, 2 versions of OpenMPI. The operating environment is Red Hat Linux version 6, except for the GPUs, which are still version 5.6. We're still waiting for the right drivers there. As I mentioned before, GPFS parallel file store with phenomenal throughputs is very useful for staging your data in and out of high-performance computing. So we're getting, what is it, about 1.33 gigabits per second back to the storage, to and from the storage. Is that about the right order of magnitude? I think it is. So I can read and write, I think about 1.3 gigabits per second.
Oh, it was gigabyte.
Gigabytes, okay, per second, which is quite good. So that's being written out in parallel or read in parallel, and it's really useful for staging in and out lots of data to the compute fabric. We have a grid submission client. If you like the sort of more easy to use or desktop version of high performance computing, it's possible for us to put a little widget on your desktop that allows you to submit jobs from a Windows machine into the cluster using grid submission tools that we build. You can use the same tools to submit to Canterbury's machine as well. It hides details like authentication and file upload and download, and some of the scripting can be hidden behind the scenes. Have any of you here used that? You seen that stuff? If you are interested in it, talk to Sina afterwards. He knows about that. And you can come down and talk to our developers too. We develop it here in Auckland, so Marcus is the guy to come and talk to. Those of you who want something more high-performance computing in its flavour, the job submission environment that's native on the IBM equipment is a thing called Load Leveler. And Gene is the person who is our expert. Expert's perhaps too strong a word. It's probably not fair because he's not been using it for that long. But he knows how to write load leveler job submission scripts. It gives you much more control to scheduling onto the IBM platform if you go to it native. And so that's what Gene can help you with. Talk to him afterwards if you want more information. This is a job submission script for a GRISU. Typically we write this for researchers so that if they want to run an R job using certain data, pulling data from a certain place, putting the results back in a certain place, we typically write the scripts for them and help them get started that way. We would do the same for people here if you want to use this kind of an environment. We have a data fabric too. This might be interesting for you guys because I know you collaborate with folks around the world, particularly in Oxford, right? Our data fabric is an IRODS data fabric for sharing large data collections interactively and managing them well between multiple sites. We currently run an IRODS data fabric which is run between Canterbury and here, so it's fully mirrored. Whatever's at Canterbury is mirrored here, so it's fully replicated, and it's on fast storage, at least here, so it will run very quickly. With fast connections to Karen coming up when we move to the new data center too. So you'll be able to get very fast throughput from the data storage that we have through to Karen and then on to wherever you need to send it. Because it's a managed service, then we can deal with replication rules and update rules and groups and security and whether data is or isn't replicated across various different sites. We support, I think, more than 70 folks on the data fabric right now. And we have set it up, for example, it was used by the New Zealand Defence Force during the 2 big disasters down in Christchurch. They used us to move their data between here and Christchurch. And we mounted a lot of the aerial imagery and LiDAR data used in the earthquake response through our infrastructure and back down into Christchurch. iRods is, anyone heard of iRods? Come across that before? It's what a lot of the large cyber infrastructure groups are using to share their information across multiple sites. So it's being used in a lot of very large research experiments already. It's fairly robust technology. It allows us also to mount access points to iRods on your desktop, whether you're a Windows user or not. You can see it as if it were virtual folders on your desktop. It stands for Integrated Rule-Oriented Data System, and there are some of its server-side characteristics. So it's quite robust. If you're in the habit of sharing data collections with other researchers and you want it to happen fast in a controlled way, so that you can replicate or duplicate or not data around the globe, then this might be a good technology for you to use. It also allows you to go and get at the data via a web. It uses a thing called two-a-query authentication, which means your web credential, your UA credentials will get you in and out of it. It uses all kinds of other technologies to allow it to integrate with your desktop environment, and the way you might try to use it from however you use data. Rob Burrows is our lead on the data fabric. Some of you may know Rob. Again, you can get in touch with him directly or via me if you want to experiment or find out more about the data fabric. So I think that sort of concludes really what I want to say. Maybe if you have more detailed questions about becoming a user or whether we can run certain environments, what that might be like, please do stay behind and chat to us. There are some contact details here. I can leave the slides behind too. I don't know if you can you share the slide deck? Yeah, you can share the slide deck, so contact details in here. There's our wiki again. There's the Centre for E-Research website. And there are our 3 email addresses. If you want to contact us, please do. So thanks for your attention. We'll take questions if you have them, or if you want to stay behind for discussion, we'll do that. Thank you. Yeah.
The cost. Is there
The
any
cost.
to any
The cost, right. It's a little bit complicated. So if you think about it this way, the government has basically put half the money in, and the universities have put half the money in. So at our particular institution, we've bought half of it, and the government's bought half of it. The half that we've bought is for University of Auckland researchers. Okay? If you're doing commercial research, we might expect you to put some money in. But if you're doing research, no, you get access into that internal part of the NeSI infrastructure. And about half of our cycles are reserved for that, in fact, just over half. The merit access part is the part that's been bought by the government in advance, effectively. And if you're using that part, you might get an even better level of service, actually, because we won't allow that part to become oversubscribed. So if you go into the merit part half, then we're expecting that you might pay 20% of the cost. Still means that for $20,000 you can buy an awful lot of compute hours, compute hours, because our hours aren't that expensive. Right now, if you have a merit research grant at the University of Auckland, you have a HRC or a Marsden or something like a forced grant, that's going to count as merit for this first couple of rounds of merit access proposals. We have those going on at the moment. So what that means basically is if you have any funding from anywhere, even if you can't give us any of the money, right now we'll still allow you to be a merit user. over time, we'd expect that if you were a funded researcher, you might put 20% of the cost of using that infrastructure into your grants when you put them in, so that there's a signal coming back to the government that researchers do like this and they are prepared to put aside some of their research grants to help fund it into the future. So we're only asking, the most you're asked to pay is 20% of the cost, the least you're asked to pay is nothing. We can accommodate both right now.
And are you happy to support students, so postgraduate students?
Very happy to support postgraduate students, yes. If the students are doing coursework, no.
Okay, yes. No, this is for their...
It's not for education, but if it's for PhDs, we would love to support PhDs.
Right.
I know you've got around 100 research students in ABI. We'd love to support them all. So bring them along. As long as they're not doing coursework, we'd like to support their needs, yes. Absolutely. Is that sort of clear on the who pays and who doesn't? It's free for anyone who's at Auckland, unless they're doing commercial work. But what we would like is to see some of the researchers at Auckland move into the merit queue, which means you get preferred access, a higher level of support perhaps, and you might pay 20% of the cost, but not necessarily straight away. So if you have research funding right now, even if you don't have money put aside for high performance computing, we'll still find a space for you right now. Not sure how long that offer will last for, probably only a few months. At the moment, we have, what's our uptake? It's roughly about 30%
You mean usage?
capacity, yeah.
It depends. Right now we're running at about 85%. But what we do, and it's probably worthwhile mentioning, is that if you go through the merit queue, there are certain limits. Thank you. There are certain limits that we place on regular users, so to speak. For example, you cannot run huge jobs that will take the whole cluster. If you're a merit user, this limits this all. So basically, if you're a merit user, you have more potential to run. And as I said, at the moment we're running at about 85% of the capacity. Previous month we were running close to 100%. Now it's getting a bit slower because breaks are nearing, and etc. etc. So it does mean that you will have to wait for weeks and weeks and weeks to get your jobs done. It just means that there will be a short delay. For example, if we're at 100% of capacity, your job will be queued, and then it will get executed once there's a slot for you.
It's fair to say that the uptake has varied from anything from about 10-15% in the early months right through to about 100%. We've had a month that we were running at 100%. As I said, we're doubling the capacity within the next month, so we expect that would be 50%. We've got 50% more we need to fill up. Hence my trip up the road to talk to you guys.
How do you set up your queues? Does people need to know how long their job's going to run for?
That's a very good question. We try to educate our users about proper use of queuing system, and proper use meaning that there are certain limits that people should be aware of, but there are not only limits but also a fair use policy, so to speak. Because if you configure a job in non-optimal way or far away from optimal, it means that not only it will hurt you, it will hurt your colleagues. For example, when you set wall time, that is a time you expect your job to run, it doesn't mean that we expect it to be the second precise to how long the job will run, but the closer you are to the real length of your expected job run, the better we can slot you into the schedule. So the more precise you are, the better our scheduling becomes. That's short.
Can't you underestimate? Does it kill you?
No, it won't kill us. It will just get our queues a bit longer. That's it.
That's the classic one. Overestimate to make sure it doesn't kill you.
Probably the best example would be the scheduler that will run the particular configuration is called backfill scheduler, which means that if you have a huge backlog, for example, and there are jobs running, the top dog job the one that is scheduled to run next, might wait for like 200 cores, but there are only 100 cores available. So the job should wait for another 100 cores, with the first 100 to be reserved for it. Rather than wasting this 100 cores, we can slot in short jobs and let them run before the big job runs. That's why proper wall time is very important, because if you say, oh, I'm going to run the job for 3 months, and you're going to run it for just 1 hour, you lose your chance to be slotted into this point.
Thank you. We try at the moment to run a very permissive queuing system. You could contrast it, for example, with NeSI, who have some pressing needs to run climate forecasting models every 6 hours. I think they run them 4 times a day. So everything has to checkpoint out at that time 4 times a day, and nothing can run for more than 6 hours before it checkpoints out. And that's just an operating principle that they've taken on. In our environment, you can run for months. At the moment, we're running an outage every month, but we've run for 3 months without outages. So if you really need to run a small number of cores for 3 months, yeah, we could support that. We also even have some researchers who have no idea at the beginning of their compute how long it will take or how much memory it will need. And we still try to accommodate that. Sometimes it's hard, but we do try to. So we haven't adopted a very stringent policy there, because we're trying to deal with a really broad church of users, and some of them need quite permissive scheduling. Any more questions?
Yeah, your head nodes. How big is a head node?
The head node. How big is the head node?
Well, it's a fairly complicated question. In our plans, head nodes will be virtual machines. So basically, we will spawn virtual machines as we fit. So we wouldn't be oversubscribed with login nodes. Because of limits of current software that we have, we are forced to use a physical machine as a login node. So basically, at the moment, our login node is a physical machine with fairly high capacity. It wouldn't last long, so that's why we prefer to inform users that they're not allowed to run any high compute on the login nodes. But login node is very different from the head node. We have separate login node, build node, and head node.
Do you have any nodes reserved? I mean, if you were to do development and debugging and stuff like that, it needs to be interactive rather than batch.
In a way, it is supported by our scheduling policy and scheduling limits. We have, for example, we have 3 major queues, major classes of jobs. Short jobs, which will run under 1 hour, can take the whole cluster, which means that even if we give away the whole cluster, we should wait for at most 1 hour to get some cores back. Medium jobs that run up to 1 week can take only 75% of the cluster, and again, which gives us 25% of free or relatively free capacity, which means that if we need to debug something, we can reserve some nodes for our use. Also, load level supports reservations, which means that we can reserve a certain number of nodes for our own needs, starting from that point of time to that point of time. And definitely, if there is a need to do internal debugging, we can take some of the nodes off the load level circulation and use them for internal needs. But it happens very rarely.
Something we could support, or if you want Bionode to run like that, we could look at see if we could support that.
Yeah.
I was just wondering, can you run virtual machines of other platforms, like run a virtual machine?
Back to you.
Yeah, good. This is a difficult one. I think the answer is probably no within NeSI, at least for now. We run some VMs within the NeSI infrastructure, which are mostly to help facilitate the infrastructure per se, so to run the iRODS data fabric and to run the database that gathers information about jobs and that kind of things, and the job submission infrastructure. So we're not trying to support science VMs, particularly not on the cluster. My group do support science VMs as part of Best Grid, which is an older project, and for the Faculty of Science we also support some of that kind of infrastructure. So it's outside of the NeSI camp. We've experimented in the past with running VMs on nodes inside of a high-performance cluster, but we get such a performance hit for doing that that it really isn't sensible to do so. I hope that in the longer term we will have a research VM infrastructure. Again, may not be in NeSI, but there's a need throughout the university for supporting what you might call science-grade VMs. And we really don't have as an institution, we really don't have a good solution for that right now. It's kind of a work in progress, but not in NeSI.
The other thing is, we're actually developing code bases, and we've set up a system whereby we automatically compile and test, run certain numerical tests on the latest version of the code on a daily basis. So we call the things that do those compiles and run those tests in build state. Would that be something that would you be open to having a build state posted on?
So you're saying your sort of build test cycle is done daily, locally,
yeah,
and you wonder
yeah.
whether that could be ported over.
So sort of the rationale there would be that it actually helps us get to the point where we're checking that the latest version of a code base actually always runs on the
Sure.
on the NeSI camp.
I guess we'd have to have a look at what was in that workflow to see if it could be ported over, but from what you said, it doesn't sound any different to the example I showed you earlier with Jack Flanagan's work. And if running it locally, running it on the cluster every day was useful to you, yeah, we could have a look at that.
Well, basically our rationale there is that we try compile and run it on as many platforms as possible, and pretty much each platform that it compiles and runs on a daily basis, we get a green light. We sort of have a confidence level that it's still good for that platform, so it's one of the ways of getting us up and running, I think.
I guess in our model, because of our cluster being targeted to one particular platform, we support only Red Hat 6 or whatever platform we run on the cluster at the moment. All our compilation and build process is based around the currently supported platform.
I think that would work though.
Yeah, but definitely, once you are on the login node, and login node is it's just necessary access, so you can go there, you can build your software there on the login node, or in the future.
If building all the software is one aspect, obviously it's quite a big compile, and then the other one is the running of all these environmental tests.
Definitely, you can automate the process. What we do, and we do it for our own needs. We build our software, and we simply submit a test run. So test run goes to the cluster. Once it gets executed, it signals back that it's all okay, and that's it. We can even build on the cluster. We tried it. It works. It's just a matter of choice whether you choose to build it as a job.
Now, I know also that some of the computational modeling you guys do is pretty advanced stuff and involves integrating multiple models. Another thing we might possibly explore is there part of that could be offloaded to our infrastructure rather than try and port the whole thing at once? Are there stages that would make sense? We'd be interested in looking for a large parallel compute job, but also, as you can probably tell, we're equally well set up to support millions of small, embarrassingly parallel style compute. In fact, we would love to have some low priority, embarrassingly parallel jobs. We'd love to offer SETI at home for bioengineering on our facility, because that, apart from helping you guys, hopefully, would mean that all our cycles were used. And that would be just wonderful, to be able to report to my Vice-Chancellor and to NeSI that every single cycle is being used is a phenomenal place to be. So yeah, if you've got complicated tasks that are embarrassingly parallel that could be run in the background, we'd love to take those.
What about if you're using the data fabric to share data within some NeSI infrastructure? If you actually wanted to make that data publicly available,
Yes. Can that be done?
Yeah.
So the question is, can you use the data fabric to make data publicly available? Yes, you can. You can control who gets access to the data, and it can be completely public if that's the way you want it to be.
And is that accessible then just standard web browser? Or?
Yes, can be, yeah. And from a desktop, there are various little plugins like Fuse you can use to use the fabric from your desktop.
And you're happy that that data can be used for, you know, archive effectively or database type stuff, or is there going to be some sort of...
I would say that ours is not an archive. This is for projects that are active and want to be able to share data in a more efficient manner. So I wouldn't say this is where you put your data to get it archived. It will be backed up. It currently is not, although it is rated. We will run it through to TSM, tape archiving, in ITS, but there are questions about whether that has enough bandwidth to back up a very large store that might be changing regularly.
Sure.
So it's not an archive.
Sure, but for, say, a active project,
Yes.
but obviously has large data storage, for example,
Yes.
there's ones in the institute like the Cardiac Atlas project. There's
Yes.
a lot of things that are being used by the people, and people would ideally contribute to those repositories. Is that the sort of thing that could be done?
Yes, that's exactly how it's being used. Yeah. Various groups from around the country, or it could be around the world, are using that to share information. Yeah.
And is there a cost to that, or is that just part of the deal?
Is there a cost to that? It would depend probably how many terabytes you want. But if you want a lot, then I suspect we would probably need some money for that. We're not into making a profit, so we would charge you the cost to us. If you just want a small number of terabytes, then we might be able to help you. Our limit for a particular user is quite small. It's a few gigabytes. 30 gig, is it?
On Data Fabric?
Yeah,
Or
on Data Fabric.
We don't have particular quota at the moment. We do watch the usage.
Yeah.
So if the usage goes above a certain figure, and the certain figure means that we can see that it's actively growing, we can get back to the user and ask to lower the expectations, so to speak, if it hasn't been prearranged. We have groups that use 5-6 terabyte for shared projects.
There's a group down at Otago that have a national focus group on it's MRI scan data, isn't it? Brain scan of some kind data that they share with various collaborators around the country, and that's on the data fabric.
So if you want to share data, it's a good place, especially if you share data between multiple universities. It's very convenient.
Yeah. At the moment, we're serving up parts of the GPFS data using iRods, or we plan to. We can serve up block storage too. So if you want to share data, but you don't want to pay the massive cost of GPFS hosted data, then we could still help.
Are you guys considering, say, exporting your disk to us so we can access on our system?
How do you mean exporting our disks?
NFS export.
The cluster one, or Data Fabric one. The cluster one, no, we don't export it, but you can use multiple. You can use multiple ways to access data. You can use SCP, definitely. You can use SFTP. You can use Grid FTP for high performance transfer. You can use WebDev. What else?
But more like working on the...
Yeah, there's no NFS export. There's no direct access to... There's no direct access to our storage, simply because security is quite a high thing in the cluster. But rather than that...
We certainly do figure out with users how to get their data in and out, so if that's the issue, then yeah, sure, we can do that.
It depends on the volumes, because if you need really high volumes, like moving terabytes of data within the shortest period of time, there are ways to do that. There are parallel transfer mechanisms that we can use. I just want to let you know that this new tranche of hardware that we are about to receive will have new CPUs on board, Centibridge Intel, with high bitnicity vectoring operations. So some of your codes might benefit greatly from it, and better cache handling as well.
Some of the benchmarks for when that optimization is working are really, really positive.
Yeah. Even without it, you can get up to 30% performance just for cache. Yeah. It's very good.
As far as like getting set up and general questions in the future, is the wiki place to go for that?
Or people.
Just start emailing?
Yeah, I mean, you can come down the road. We're at 24 Simon Street. That's the building that used to be ITS. So come and see us at 24 Simon Street, the building that used to be ITS. It's now security when you approach it from the front, just before you get to engineering, but you actually go around the back of that building where the audiovisual library is, and our offices are there. You'll see a sign up on the door.
The process of joining is very easy. You just have to fill out one form, and that's it. We approve your account within an hour. Data Fabric is easy. You just go to the website and you automatically get registered there. You have open API.
It's pretty easy. We've helped a number of people get set up so we know about where the pain points are. And we just need information about what code you need and how your data's going to be staged in and out. And, yeah.
Regarding, I mean, so quite a few people here who use homegrown CA and OpenCA where they do a lot of build. Now, with that, we have a lot of requirement on certain versions of libraries and stuff. Who do we contact?
Contact any of our people. We see that Yuri.
Ben, anything with libraries and getting your workflow set up. I mean, every researcher we help who has HPC codes has the same issue. So we've figured out how to do it for most people who come to see us. So I think we can do it. Yeah, okay. We'll end there and devolve into more friendly questioning if you have any more questions. So thanks, guys.